Welcome to Linear Programming and Applications. Today, we are diving into a fascinating mathematical trick called artificial variables. If you have ever wondered how algorithms like the simplex method handle complex, messy real-world constraints, you are in the right place. Let us build our understanding from the ground up. To understand why we need artificial variables, imagine you are trying to build a brick wall on uneven, sloped ground. You cannot just lay bricks on the dirt. The wall will collapse. First, you must build a temporary wooden scaffold to give yourself a perfectly flat, stable starting line. Once the bricks are secure, you remove the scaffold. The simplex method works exactly like this. It is a mathematical machine that builds the optimal solution step by step, but it absolutely requires a perfect, ready-made starting point to begin its work. Now that we understand the need for a starting point, let us look at how we create one mathematically. Sometimes our linear programming problem does not naturally provide this perfect starting point. When this happens, we invent a temporary fake variable to act as our scaffold. We call this an artificial variable. It is a non-negative variable added to the left side of a constraint equation. Its sole purpose is to help form an initial basic feasible solution, giving the math machine a place to start. But remember, because it is fake, we must force it to disappear before reaching the final answer. This concept leads us to look at a standard constraint that causes trouble. In many problems, we have a minimum requirement, represented by a greater than or equal to sign. Here, x1 and x2 are our main decision variables, representing things we want to produce. The total combination must be at least 10. If we increase x1 or x2, we easily meet the requirement. However, to use our mathematical machine, we must turn this inequality into an exact equation. The simplex method cannot work with inequalities directly, which sets the stage for our next step. Before we move on, let us see this with a concrete example. We are given the inequality and asked to prepare it for the simplex method. First, we subtract a surplus variable, s1, to make it an exact equation. S1 represents whatever extra amount we have above the required 10. But here is the catch. The simplex method always starts by setting the main decision variables to 0. If we set x1 and x2 to 0, the equation leaves us with s1 equals negative 10. This violates the strict rule of linear programming that all variables must be positive or 0. We are stuck. To fix this broken starting point, we introduce our mathematical scaffold. We add an artificial variable, a1, to the left side of the equation. Now, we again set our main variables, x1 and x2, to 0. We also set the surplus variable, s1, to 0. This leaves us with a1 equals 10. By doing this, we have created a valid, positive starting point out of thin air. The artificial variable acts as a temporary placeholder, providing the positive value needed so the simplex algorithm can finally begin running. Now that we have used this trick on a single equation, let us understand the broader goal. The simplex method needs a starting set of variables that perfectly match the number of constraints in the entire problem. More specifically, these starting variables must form a clean diagonal pattern of ones across the equations. Mathematicians call this an identity matrix. Every row must contribute exactly one positive starting variable to this matrix. If a row naturally provides one, great. If it does not, we must intervene mathematically to ensure the identity matrix is complete. This requirement for an identity matrix brings us to a full system of constraints. Here we have two constraints that we need to format for the simplex method. The first equation represents a maximum limit, like a budget, indicated by the less than or equal to sign. The second equation represents a minimum requirement, indicated by the greater than or equal to sign. If we increase the variables in the first equation, we get closer to our limit. If we increase them in the second, we exceed our minimum. Let us see how to handle both types together. Let us process this system step by step, starting with the first constraint. We are given x1 plus x2 is less than or equal to 5. Because it is a less than or equal to type, it only needs a slack variable s1 to take up the leftover space. A slack variable represents real unused resources. When we set the main variables x1 and x2 to 0, s1 naturally becomes 5. This is a perfect positive starting point for this specific row. No fake variables are needed here. Now we move to the second constraint, which is greater than or equal to 8. As we learned earlier, we first subtract a surplus variable, s2, to make it an exact equation. But setting the main variables to 0 would give s2 a negative value, which is not allowed. Therefore, we add the artificial variable a1. Now, if x1, x2 and s2 are all 0, a1 equals 8. We now have our starting variables for the whole system. s1 equals 5 for the first row and a1 equals 8 for the second row. The problem is ready. We have seen how to handle inequalities, but this brings us to another scenario, exact equalities. Sometimes a problem gives us a constraint that is already an exact equation. Because it is already equal, it does not have any slack space for leftover resources, nor does it have any surplus space for extra production. Therefore, we do not add or subtract any s variables. However, even though it is already an equation, it still lacks a starting variable for the simplex method to use. Let us look at how we solve this specific issue. Let us examine the mathematical form of an exact equality. Here we have 4x1 plus 3x2 equals exactly 12. The number 12 represents a strict requirement, like an exact blending ratio in chemical manufacturing. If we increase x1, we must decrease x2 to maintain the exact balance of 12. If we try to start the simplex method by setting our main variables x1 and x2 to 0, we get 0 equals 12, which is mathematically false. The simplex method has no single variable it can use as a starting point here. To resolve this mathematically false statement, we apply our scaffold technique again. We take the exact equation and simply add the artificial variable a1 to the left side. By adding a1, we create a starting point out of thin air. When x1 and x2 are set to 0, a1 takes the value of 12. The math machine can now begin its work, treating a1 as the initial solution for this row. This simple addition saves the algorithm from crashing and allows it to process strict equality constraints. Now that we know how to use artificial variables, we must ask, why does this matter in the real world? In real business problems, we rarely only have simple less than constraints, like a limited budget. We frequently face greater than constraints, such as a minimum production requirement to meet a customer contract. We also have equal to constraints, like exact blending ratios in chemical manufacturing. Without artificial variables, the simplex algorithm would completely crash when facing these common real-world conditions. By using this mathematical trick, we can solve highly complex logistics, diet, and manufacturing problems. Let us visualize exactly what we have built. Look at this matrix representing our system of equations. The columns represent our variables. Notice the slack variable s1 provides a positive 1 in the first row. However, the surplus variable s2 provides a negative 1 in the second row, which cannot be used as a starting point. This is where the artificial variable a1 steps in. It provides the missing positive 1 in the second row. Together, the 1 from s1 and the 1 from a1 form a perfect diagonal identity matrix, giving the simplex method its required starting grid. We have covered a lot of ground today, so let us summarize the most important ideas. First, artificial variables act as temporary mathematical scaffolds, allowing the simplex method to begin its calculations. Second, they are specifically used to fix greater than or equal to and exact equal to constraints, providing the necessary positive starting values. Finally, Always remember that these variables have no real-world physical meaning. They are purely a mathematical trick, and the algorithm must force them to zero by the end of the calculation for the final answer to be valid. You now understand the foundation of handling complex linear programming constraints.